here is page two, and therefore part two of our little adventure. So let's talk a little bit more about proportionalities and similarity. So this question four asks us to use what we know about proportions and similarity to solve the missing side length. And so again, our goal here is to first prove that these things are similar, or at least have some ideas that they are. Make sure that we have the corresponding parts lined up, probably setting a proportion, and then end up solving it. So let's jump into it. Now, we do have to assume in this case, looking at the problem again, that these are similar because they're not telling us to actually prove that part. We just have to assume they are, and it looks like they're even nicely ordered, so this should be pretty breezy, actually. So let's get to it. If these are similar, we know the side lengths have the same proportion, so what we have to do first is make sure that we have our corresponding sides set up well. And since there's no kind of trick to this particular problem, all we really have here are just a couple side lengths. So if these are similar, then 12 corresponds to 3 in the same way that 20 corresponds to x. Now you may be able to look at this and do this in your head. I'm just going to go ahead and work it out. Again, I'm going to use cross multiplication, just solving regular algebraically, because we're pretty comfortable with that. And so here we have 12x, and then here we have 60. So the question is, well, how in the world do we solve for x? Well, divide by 12 in both cases and get x to be 5. Now, in truth, we could have done that right off the bat just looking at this problem, because if you think about what it takes to go from 12 to 3, that really just takes a division by 4. And so if we take 20 divided by 4, because again, similar triangles have to have the same ratios, 20 divided by 4 has to be 5. So whether you set it up like the long way or you kind of use your intuition and solve it, doesn't really matter to us, honestly. Just make sure that you're always showing your work and you can prove that you actually know this stuff. Let's look at this guy. We want to solve for the missing side lengths. Okay, and so again, we have to maybe do some thinking work first and know that x and 3 are corresponding. The picture again, let's take it to be to scale. Now what we have to do is just figure out like a set of numbers to go with this, because we know if these are similar, the way x corresponds to 3 should be the same as another set of side lengths in this figure. Now the interesting part about this is it doesn't really matter which pair of side lengths we pick, we just got to pick them. Now that's a really clever way of saying like pick the ones that look the easiest. I would actually pick these two. 40 and 56 are fine, but those numbers, at least for me, are kind of hard to manipulate in my head. But I can tell 10 to 40 really, really quick. In fact, although I'm showing kind of a long way writing this out, we could probably just do this in our head because we're picking those numbers very nicely. So x is to 3 in the same way 40 is to 10, because we're going from this figure to the smaller one. So now let's go ahead and set up our cross multiplication and solve it. And so we have 10x, and then 40 times 3 is 120. And so we divide by 10, x has to be 12. And again, I would claim that we could probably figure that out right off the bat, because if we pick 10 going to 40, that's a dilation of like 4. And so 3 has to undergo the same multiplication. And of course, 3 times 4 does equal 12. And so you can attack this problem either one of those two ways. It's completely up to you. We have 5 for the first one, 12 for the second one. Now we have some multiple choice, because that's kind of indicating that maybe there's going to be some multiple choice in your test. What's going on here? Zoom in like I told you to, machine. So the question here is, which of the following proportions would be correct to solve for the missing side length? Now again, we're making the assumption that these are similar. We can probably confirm that really quick. Again, we have, assuming this is a scale, we have a couple of right angles here, and then we have an embedded shared angle here. So these are similar. So we can use these principles of proportionality to solve. Now we're asked to solve for x, and so what we have to do is think about like the smaller triangle that's kind of embedded, which side corresponds to x, and of course it's going to be this one here that's 6. Now we have to match that with another set of side lengths. Well, we have 14, which is a big guy, and we have this 8, which is kind of the small one. And so setting this proportion up to actually solve, let's go color coordinated here. So we have like 6 over x is equal to 6 over x. We're going bottom of this, left of the small, left of the big. So we should go bottom small, bottom big. So I'm looking at 8 over 14. Now I don't see my choices right now. I'm just writing this because this is a knowledge that we do have, and so now we have to kind of compare that, knowing that this ratio is right. Let's now compare them with our choices. Um, Now we don't have anything. It doesn't look like anything is quite written the same way I have mine written, but that doesn't make it bad. It doesn't make the one we wrote as bad. We just have to kind of move it around. Um, so um, a thing to note here is that we do have some corresponding pieces. We do have like 6 and x and 8 and 14, but you can also say like x and 14 are corresponding, and then 6 and 8. And so that could also kind of give us what our ratio might be. A nice kind of trick to this is to think about the one we wrote and think about like rotating it. Because if we can see this ratio somewhere, like that should still be valid. 6 over x, 8 over 14, like we wrote originally, is valid. We can also look at it like this. X over 14 is equal to 6 over 8. Those are all valid ratios because they're all keeping the corresponding parts aligned. And look, would you looky here? That's just the one that I have in this spot. Okay, and so this is actually going to be our correct answer um, for this problem. We can double check it because if we think about x over 14, x over 14 is just keeping within the big triangle. Like that's the left of the big, bottom of the big. And then 6 over 8, left of the small, bottom of the small. So even though that's not the ratio that I originally picked, it is a valid ratio. Okay, here we have a very similar type of problem that we had before. We have to solve for x. Again, I'm going to ignore my choices temporarily. I'm just going to work the problem the way I know it should be worked, like just matching up the pieces using what I know about similarity. So let's get to it. So I have 5 and I have 12. Like those two are corresponding because they're both like the bottoms of the triangles. And then I have 6 and oh, they're trying to trick me. They want me to say 6 and x. But you and I both know better than that. Like 6 is the left-hand side of that triangle, which means I need the whole left-hand side of that triangle as well. What a tricky problem. Which means like this whole side is actually going to be 6 plus x. And so when I'm writing this ratio, again, I have to use full side lengths. And so I have to write something like this, where I have like 6 over x plus 6 is going to be the same as 5 over 12. Now, again, I don't know if this is the actual ratio I'm going to find in my choices, but I'm writing it first knowing that I can kind of manipulate it to make sure it matches. Uh, so let's see if this one is written exactly as I see. It's not. So again, know that if as long as I keep the corresponding pieces aligned, I should be okay. So I'm going to try this one first. Do I see x plus 6 over 12 is equal to 6 over 5? Well, number one is awfully close, but those aren't, 6 and 5 should be switched. So that one's actually no good. Uh, let's see. On C, I have x plus 6 over 12, and I have 6 over 5, just like I have in my example. So that's going to be my answer. And we can double check. It's not the original ratio that I wrote, but that doesn't make it wrong. X plus 6 over 12. That's just like the left-hand side of the big, the bottom of the big. 6 over 5, left-hand side of the small, bottom of the small. So that ratio is going to match as well. Okay. All right. We're kind of, oh, this is still a dilation question. So it's related, but now we're kind of switching gears. We're actually now going to be doing some dilations. Do recall dilation works the same way as similarity. The side's just getting bigger or smaller by a certain factor. In this case, they actually tell you what the factor is. It's going to be a half. So there's a couple ways we could attack this. The first thing we could do is actually just try to grid this out. But I want to take and do more like a guess and check. But I want to do something maybe a little bit more studious. I want to make a list of vertices. And what I mean is this. So we have this A, and A is coordinated at 1, 3, 4, 5, 2, 3, 4. Okay. So A is coordinated 5, 4, negative 5, 4, excuse me. B is coordinated at 1, 2, 3, 1, 2. And then C is coordinated at 1, 2, 3, 1, 2, 3, 4. Negative 3, negative 4. All right. And the reason I'm doing that is it's going to give us a way to kind of check this at the end. So like we'll go ahead and do the work on the dilations, dilating by half, but in the end we should be able to check our coordinates and make sure that we did this correctly. Now there's a little wrinkle in this problem, and the wrinkle is that we have to take a center at D. If the center was at the origin, I could just like cut all these coordinates in half. I could just multiply the coordinates by the k factor. Um, and then that would put my coordinates at the right place. But that's not going to be the case here since D is not the origin. And so I could say do some shifting around and redrawing this, dilate it and move it back. That's really complicated too. I think the best way we can attack this is really just to do some counting. Let me explain what I mean. So a dilation is just taking half a distance of something. Now you guys have experience with midpoints, taking distances on the grid, so this should be no big deal. And again, since the k factor is such an easy one like a half, we should be able to take a counting routine and make this happen. So consider this, from D to B, from delta to Bravo, I have to go over 1, 2, 3, 4, 5, and then up 2. Well, if I want to cut that in half, I can just cut that journey in half. So 1, 2, 3, 4, 5, 1, 2 turns into 1, 2 and a half, 1. And that should be my new point. To coordinate it, this is going to be 1 half, comma 1. And if you look at our coordinates of B, we can actually see this in action. And so like if you look at the coordinates of the green and the red, it should make sense that that should be half the journey. But we can do that with all the points actually. So if we take the journey from D to A, delta to alpha, we have to go over 1, 2, 3, and then up 1, 2, 3, 4. So if we're dilating by a factor of a half, let's just do that by half. And so, oops. So instead of going over 1, 2, 3, we can go over 1 and a half. Instead of going up 1, 2, 3, 4, we can just go up 2. Okay, so new coordinates for this should be 1, 2, 3 and a half. Okay, and then 2. Okay. Okay, so last one, D to C, I have to go down 1, 2, 3, 4 over 1. So if I go down 1, 2 over a half, that should give me new coordinates at C at negative 2.5, negative 2. Now when we draw this new shape in, okay, when we draw the new shape in, we can confirm that this is a good dilation for a couple different reasons. One, with a k factor of a half, we know the thing is going to get actually smaller. And it certainly has. The other thing is we can actually look at this and know that these are parallel. And so if we kind of look at the slopes from A to B and from A prime to B prime, we can see that we actually have the same slope value. Same thing if you look at the slopes down here to C prime, which is one of the characteristics of a dilation. So we have the center at D, we have parallel lines that are in due dilation and smaller. We should have high confidence this is correct. All right, so that is part 2 of the key series. I'll see you guys in 3.